Probably the most important structure that we're going to discuss in this course is a structure called a vector space. And we're going to start by considering one example of a vector space, which is the space Rn. And I'm going to describe it and tell you what it is, and then we're going to kind of try to figure out what its properties are, and then we're going to make that abstract. That's the idea. So what is Rn? So by definition, Rn is the collection, the set, of all vectors. Remember that a vector is a matrix with only one row or only one column. That's how we thought of them. So I'm going to write it as a column vector, but you could write it as a row vector. It doesn't really matter. All the column vectors of the form A1, A2, ... all the way to AN. So there are n entries here in this column vector, such that all these elements are taken from the field R, the field of real numbers. So remember the notation, the set of all vectors, column vectors with n entries, such that all the AIs, all these entries, are just numbers from the field R. So that's the set Rn as a set. Often you'll see that these column vectors are called N-Tuples. Okay, sometimes they're called that. Okay, so these, maybe let's write that. So these are called vectors, column vectors. You could write them as rows, or sometimes called N-Tuples. Okay, so what is the structure on this space? We're going to call it a space. What is the structure on this? Well, we know how to add things like this, right? So if we denote, let's maybe even start with equality. When is A, so when we put an arrow like this stands for the entire vector. We use this notation previously when we discussed matrix form of systems of equations. So when are two vectors the same? When is A equal to B? If all the entries are the same. So AI equals BI for every I. That's when two vectors are the same, right? How do we add two vectors? So A plus B, how do we add them? We just do it component-wise, right? We add each AI with the appropriate BI. So A plus B is just going to be the vector that has A1 plus B1 in the first entry, A2 plus B2 in the second entry, all the way up to AN plus BN, right? That's how we add vectors. We also know how to multiply a vector times a number. Okay, so if alpha is a number, not R, how do we multiply alpha times a vector? We're just borrowing the ideas straight from matrices. These are matrices. So alpha times a vector is just alpha times the first coordinate, alpha times the second coordinate, and so on, all the way up to alpha times n. Okay, so we have two operations here. One is the addition of vectors, and another is kind of a weird operation because it's not an intrinsic operation to vectors, it's rather an operation between vectors and numbers from the field, which are called scalars. Okay, so this is what's called scalar or scalar multiplication. No, that's bad terminology. Multiplication by a scalar. I'm being careful about using the term scalar multiplication because further, we're not going to discuss it now, but there's a concept called a scalar product, okay, where you do multiply two vectors and you get a scalar, but that's irrelevant to what we're doing right now. So let's call it multiplication by a scalar. By the way, this word scalar just means a number. It just means an element from the field. So here our field is R, so these alphas come from the field R. But the reason they're called scalars is because what we're doing is we're scaling the vector. So if we had a vector, multiplying it by 2 is scaling it by 2. And we'll see the geometric interpretation of this in a minute. And that gives more meaning to this idea of scaling and multiplying by a scalar. Okay. So we have here what? We have a space Rn. These are just, it's a set of elements. And we have two operations on it. One is this plus, addition of vectors. Okay, addition of vectors. And there's the other operation, which we denote by maybe a dot, but actually we don't write the dot often, okay? We just eliminate it. So this triple of a space with these two operations, addition of vectors and multiplication by a scalar, this structure, now it's a structure, it's not just a bunch of elements, it has some structure on it. This thing is called, no, it's not a field, the field is R. Okay, this is called the vector space Rn. That's what it's called, the vector space. It's a space of vectors. Okay, so let's try to see what properties these two operations have. Okay, I'm just going to make a big list of them. So, for example, so let's write properties.
I'm sorry, is it called the vector space or the vector space Rn?
The vector space Rn, that's what I wrote. Okay, there are more vector spaces, and that's the broader concept that we're going to discuss later. This is just the first one, an example. Okay, so properties. So for example, maybe something trivial to say, but we'll see that it's very important. If we take two vectors, A and B, elements of Rn, this implies that if we add them, which one do I want to do first? Yeah. If we add them, the sum is again a vector in Rn. Okay? We're adding two things, we're getting something of the same nature. Right? Do you agree? Okay. Here's another property. If we take a vector in Rn and the scalar in R, then the scalar times the vector is what? It's a vector. It's not in the field. It's in the vector space. It's in Rn. Do you agree? Okay. So these two properties share the name closure. Closure of the set under the operations. This property means that it's closed under addition. We're adding things, we're remaining in the same set, in the same world. This means that it's closed under multiplication by a scalar. Okay? So these are two properties of closure. Okay? Some more properties, well-known properties. So for example, we know that if we add two vectors, it's just a special case of addition of matrices, so we know this. Or you can see it that you're adding component-wise, so it doesn't matter if you do 1 plus 2 or 2 plus 3 for each component. So we have this commutativity property for the addition, right? So this is the commutativity of addition, of vector addition, right? Property number 4, we have the associativity of vector addition. If we take 3 of them and add them, it doesn't depend on which order you add them in. So you can first do A and B, or first do B and C, you get the same thing. So this is the associative property. Good? Okay. property number 5, there exists, remember this symbol? There exists a 0 vector. A 0, and I'm going to add a little arrow over the 0 to indicate that it's the 0 vector. Namely, it's just the vector that has 0 in every entry. So there exists a 0 vector in Rn. And what does this 0 do? What is its special feature? That when you add something with a 0 vector, you get back to something. So such that a plus 0 equals a for every a in Rn. Do you agree? Okay. Good. Next property. Note that all the properties so far, well, except maybe number 2, all the properties are first properties of the addition. Okay? We're going to then reveal some properties of the scalar multiplication. So, number 6, for every, we even have a symbol for that. For every a in Rn, there's an additive inverse. There exists, remember, for all or for every, there exists a minus a, which is again an element in the same vector space. What is minus a? You just throw in minus signs on all the entries, right? Such that, what is the property of the additive inverse? What does it do?
A plus minus A is the 0 vector.
Right. A plus minus a gives you the additive identity, gives you 0. Right? Okay. 4 more properties. We're going to need another board. Property number 7, 1 times a equals a for every a in Rn. What is this 1?
Scalar.
Right, it's the scalar 1. It's the number 1 in the field. Do you agree? We don't know, we haven't defined any notion of multiplication of vectors. Okay, so putting an arrow here would not make sense. Okay, but if you take the scalar 1, it satisfies that if you multiply it by any vector, you're just multiplying each entry by 1, so you're not changing anything. Okay, good. And now 3 more properties, which I really, really want to fit on this board, and I'm going to do it. So I'm going to erase here and erase here a bit and make room here for 3 more properties, which are all involve the scalar multiplication and the addition. So property number 8, alpha times a plus b equals alpha a plus alpha b. What would you call this property? Right, distributivity. And 9 is going to be that alpha plus beta times a vector a, now we're adding scalars and multiplying them by a vector, equals alpha a plus beta a. What would you call this property? It's also distributivity. Okay? It's distributivity is a property that relates addition to some form of product, to some form of multiplication. Okay? These 2 pluses are very different pluses. This is a plus of vectors. This is a plus. It looks the same. I mean, even from here, it looks precisely the same, but it's a totally different operation, right? This is a plus of numbers, of scalars. And here we're distributing the plus of addition of vectors with respect to the multiplication by a scalar. Here we're distributing the plus of addition of scalars with respect to the multiplication by a scalar. Okay? So both 8 and 9 are forms of distributivity. So let's add here for 1 and 2, these are the closure properties, 1 and 2, and let's add here, not sure I'm going to be able to do this, but I'll try this, Distributivity. And this U is a V. Good?
Do 5, 6, and 7 have names, like the properties?
Yes, it's the same names that we've discussed before. This is the additive identity, we mentioned it. This is the additive inverse, okay? It's the same names, the same sort of properties that we've encountered when we discussed fields, okay? Okay, one more property, property number 10, says that AB times A, sorry, alpha beta times A, where alpha beta are scalars, equals alpha times beta A. Okay, so these, it's sort of an associativity property, but with respect to two different operations, right? Here, it's a product of two scalars, of two numbers, whereas here, it's the product of a scalar times a vector. Do you see that there are two different notions of multiplication here, both of which do not have a symbol at all, but they're different? Do you see that? Okay? Good? Okay. So for all of these, maybe you should add for every alpha beta, for all of these three, for every alpha beta in R, and for every A and B in Rn. This relates to all these three properties. Okay?
That's the last property equals alpha times A with parentheses times B.
Yeah, you can add that. You can multiply alpha by A and then multiply by beta. It follows, you don't need to write it explicitly because it follows from the fact that you can commute the multiplication of the scalars here, right? And then just use this property again. So I'm not going to list it separately, but it's true. Okay? Okay. So these are some properties. We just collected things that are easy to observe that the vector space Rn satisfies. Okay? Do you agree? Okay. And where are we heading? So what we want to do is to say there are many, many, many things in mathematics that satisfy these 10 properties. Okay? Some of them you know very well. Maybe you haven't thought of it. Okay? And we're going to talk about it shortly. But many different mathematical structures, like functions, like matrices, like solutions to homogeneous systems of equations, many, many things satisfy these 10 properties. So we want to strip these 10 properties from their concrete vector space Rn and say, hey, let's define an abstract notion, a general notion called a vector space, where Rn is just going to be one example of such a thing, and we're going to call it V, capital V, for vector space. And what is a vector space? A vector space is a bunch of elements that satisfy a bunch of elements, plus a field where you take the scalars from, plus an addition operation, plus a product of elements from the field times elements from V, that satisfy these 10 abstract properties. Okay? It's going to look very abstract. Very abstract. Okay? But then we're going to see that, in fact, we're just rewriting these 10 properties that we know that N-Tuples satisfy. Okay? And then we're going to see in examples that, in fact, many, many other things satisfy them. And why is that good? The reason it's good is, if we prove a theorem about a vector space, well, one reason it's good, if we prove a theorem about a general vector space, it automatically holds for all the examples. For Rn, for matrices, for solutions of homogeneous systems, for whatever. Okay? So making something abstract has a very powerful idea behind it. You prove something in the abstract setting, you get it for free for all your examples. Okay? Good? Clear? Okay, but before we do that, I want to discuss the vector space Rn just a bit more. So what I want to say is that there's more to Rn than just these 10 properties. Okay, for Rn, and in particular for R2 and R3, we have a geometric visualization of them. We know how to think of them in terms of geometry. Okay, so for R2, which is just pairs, 2 tuples, pairs of real numbers, and R3, which is triples of real numbers, we have a geometric point of view, a geometric realization. Okay, so we don't just think of them as algebraic, mysterious things. We actually think of these vectors, and I'm quite sure you've seen this. We even mentioned it when we discussed complex numbers. You think of them as arrows, right? So, for example, R2, we think of the plane, which we often indicate like this, and the elements we think of as little arrows. Okay, so if you have what is an element in R2, it's just a point A comma B. We think of A as the x coordinate and of B as the y coordinate, and here's a point in R2, right? This is A comma B. We can write it as a row vector or a column vector, it doesn't matter, right? So this is a point in R2, and furthermore, we often identify this point with an arrow that starts at the origin and ends at that point. Do you agree? Okay, maybe I shouldn't call it AB, but call it A1, A2. That would be more reasonable for what we're going to say in a minute. Do you agree? And then this would be the vector A. That's how we think of elements in the plane, right? And then we can have another one. Let's draw it in red. Let's say we have somebody here, and this corresponds to the point B1, B2. So this is B. And we know what this addition of, so here the scaling becomes very, very obvious, right? What is multiplying this by 3? It would precisely be multiplying the x coordinate by 3, tuck, 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 multiplying the y coordinate by 3, and getting a vector, an arrow, 3 times the length. So scaling by 3, multiplying by the scalar 3 would be precisely scaling it by 3. Do you see that? You see it, right? How do we add these guys, right? Adding vectors in Rn in general is adding component-wise, right? So we do A1 plus B1, that's the x coordinate, and A2 plus B2 is the y coordinate, and that corresponds to just taking the x component of this, adding the x component of this, which would throw us to their sum in terms of the x and their sum in terms of the y, and geometrically we know what we get. We get the diagonal of the parallelogram, right? We would get this vector here in black. This would be A plus B, right? So even the addition has an interpretation, a geometric interpretation that we can visualize, we can see. And by the way, this can be done in R3. There's just a missing axis here. Think of another axis going this way, and everything works exactly the same. Okay, the drawings become a bit more challenging, but it's exactly the same idea, right? So there's a geometric realization for R2 and R3 as what's called two-dimensional space and three-dimensional space where we all live, okay? And there's even more to it. In R2 and R3, we often define more operations, more products, okay? So for example, there's a product of two vectors called the scalar product, and there's a product of two vectors called the vector product. The scalar product can be extended to any Rn. I'm not telling you what it is right now. The vector product is something that is really intrinsic to R3. It's a special thing about R3 and cannot be reduced to R2 or extended to higher ends, okay? But we're not going to discuss them here. I'm not even going to tell you what they are. They go beyond the idea, beyond those 10 core properties of being a vector space. They give it even more structure, okay? And the rest of the things that we're going to discuss, the rest of the examples of vector spaces that we're going to discuss, are not necessarily going to have these properties, and therefore we're not including them in the properties in the properties we're trying to isolate and identify and restrict to. Okay? So I'll remark that. Further structure such as the dot product or the scalar product, also called scalar product, or the cross product, also called the vector product, the reason it's called the dot product is it's a product of vectors which we denote by a dot. And this is a product of vectors which we denote by a little cross. That's the reason for the names. Are not part of being a vector space. So I'm not saying anything of the form, these are not important. They're crucial, they're very important in applications and so on. But spaces with these further structures or other further structures are not just vector spaces. They have further structure, and it is generalized. Okay, there are things called, for example, metric spaces. Okay, metric spaces are spaces that are not just vector spaces, but they have additional structure. And this, for example, yields the metric structure, which means that you can measure distances, okay, and measure angles and things like that. Okay, so the idea of being a vector space is really just the algebraic part of these structures, namely the addition and the scaling. That's what we're considering in looking at the vector space structure of Rn. Okay, clear? Okay. Good. Yeah. So what we want to do now, what we want to do next, it's going to be in a separate video. What we want to do is take these properties, erase the Rn's everywhere, and erase the R's everywhere. Replace R by capital F, standing for a field, any field. It could be C, it could be other fields, which usually we don't discuss in this course, but we mentioned that they exist, like finite fields, Zn, and so on. And replacing Rn by something general as well, V, standing for a vector space. Okay? And that's what we're going to call a vector space. Then we're going to see many, many examples of those, and then we're going to start building the theory of vector spaces. Okay? So that's coming up next.